Well, all right, we're almost ready to wrap it up here. We're over time a little bit. If we take Heisenberg's, if we follow his lead, what are we going to do? We're going to look for observables, right? And maybe we can work string theory in a way that has to do from observables instead of going back to this Planck scale that's unobservable, right? Maybe that's possible. Well, and the measurement is the backbone of science. If we look at the measurement units now, this is the amp, this is the Kelvin, this is seconds, meters, kilograms, candelas, and moles. Those are kind of historical things, right? They're supposed to be, this is the SI system kept by the French that the whole world, all science uses, right? You will study this system. How many of you already have? Okay, so you already know about this. Well, how fundamental are these seven? They're supposed to be, but look how interconnected they are. What does that tell you? If this one's depending on these three, and this one's depending on these three, the only one that's not depending on any of them, but also that's not offering any support, is the temperature. Doesn't that strike you as weird?
And they recognize this. Those seven just developed because nobody sat down and designed it. This is like a kludge machine. What do you call it? Goldberg contraption, really. No, Rube Goldberg they call him, right? So this guy named Xavier Bohr, he's just a guy out on Malta Island, and he's an engineer. He's a pretty smart, practical guy, and he makes a simple observation. He says, look, if you look at these things, the Kelvin sitting out here is really strange. If you do a dimensional analysis, you'll find that you need to add these three arrows to it. So he added these three green arrows right here to the Kelvin. And then what that did is that told him that, hey, all of these are interdependent. And through dimensional analysis, he found out that you could take any two of them and make the others dependent upon those two. So then he said, well, if you can do that, which two are you going to choose? And so since space and time seem to be the most fundamental, right? He said, well, we ought to do that. We ought to take those and make those. So he did that. And let's see. This is showing. Yeah. Okay. So see, here's time, right? And there's two space and time go into there. Space and time into there. Space and time into there. Space and time. Space and time. But nothing coming into space and nothing coming into time. So he's made these two independent. Now I put them here together, space and time, because the only known relationship of space and time is motion. So I put them together because that fits with Larson's theory, and put them in the middle, and so now we can see how that simplifies it. Isn't that pretty neat? That's kind of a unification, isn't it? But one that nobody was really looking for, you know. But and this guy, not a real. He has his own theories, and he has his website out there. And if you Google it, he's considered a crank and a crackpot. But I don't know about his theories, but I know this is really pretty cool because look at this table. You can take any constant, you can take any term in an equation of physical constants and put them in terms of space and time. Nothing but space and time. And so if you guys, as young Heisenbergs, and that's what we're wanting to do at Larson Research Center, we want to try to somehow get you guys involved, all right, where you can come into the, if you have an interest in physics and whatnot, maybe someday you will actually be working at the Larson Research Center. Who knows? Or maybe you didn't do this without it, because this stuff is just fascinating. If you get into it, it's even better than computers and networks. But anyway, so if we're going to fiddle in that field, what's the question we'd ask, given that Bohr has shown this unification of the measurement units? Well, let's say this. If the dimensions of the gravitational constant g, as well as the quantum action h, and the speed of light c are units of space and time, then what does this imply? Does it imply something? motion. It being then that motion somehow is the basis of all. Alright? Because the only known physical relationship. Now I know that Einstein's equation, I mean, following Minkowski, they have the space, the slice of space-time and everything, and all that seems to work out. And so that way they combine space and time. But that's not the way we're combining it here. We're combining it in this equation right here. Now what does this equation tell you? This is the only known relationship, the only one we can observe between space and time. Velocity is equal to a change of space per change of time, right? Now, can we stop time from changing? I don't know how we could. I don't think they've ever found a way. But how do we get space to change?
Just set something down.
We got to change the location of some object, right? But where is the object in this equation? You see an object in that equation? There isn't anything but space and time in that equation. Changing space and changing time. We talk about the change of location as a space of time per unit. Change of space per unit time. But that doesn't necessarily mean that that's the only way space can be changed. We can observe two amazing things following Heisenberg's method of sticking to observations. One is that space is increasing all the time. And two is that time is increasing. Now, does anybody have to be proven? Do I need to prove to anybody that time is increasing? We pretty well observed that from the beginning. No one I've ever seen has been able to stop it. But what about space? Why do we say space is increasing? Is it really? Tell me, guys. Huh?
Expansion of the universe.
Expansion of the universe, right? We look out at the galaxies and what do we see? They're all moving away from us. So what does that mean? We're the center of the universe? Huh? You would think, right?
We're moving also.
Huh?
We're also
We're also moving.
moving.
Where are we moving? We're moving away. So every galaxy is moving away from every other galaxy, right? Alright, so if we have galaxy A, B, and C on a line, and observer A looks at B, which way is it going? Towards C, right? And he looks at C, which way is C going? Yeah, away from B. But observer C reports back to him and says, well, you got it all wrong, man. It isn't moving this way. Which way does observer C say it's moving?
The other way.
He says it's going in the other way. B's going towards you, A. And A, you're heading out there even faster than B's going. In the opposite direction that you're saying. And then B says, no, you're both wrong. A is going this way, and C is going this way.
Center of the universe.
He's the center of the universe, right. But if C had a D over here, you'd see that D was moving away and they're moving that way and so on. So this is what we call a scalar expansion or a pseudo-scalar expansion. Alright, it goes back to those 10 dimensions. 2 to the 0, 2 to the 1, 2 to the second, 2 to the... We'll talk more about that in the next lecture. It's really interesting. But this 3D pseudo-scalar increase has 2 to the 3 equals how many directions? 8 3D directions. They're the 8 corners of a 2 by 2 by 2 cube going through the intersection. And that's how you can describe the expansion. Whereas time, how many directions does time have? Just one. It just increases. You can't really say it right? I mean, time is 2 to the 0, which is equal to 1. So, man, that's amazing. Now remember, we're fiddling around here, see? So, we could come up with a new idea. We could start with this space-time expansion. So when we have a change of space, d, it comes out blurry, but the d of s to the third power and d of t to the zero power, and we have an equation of motion without anything moving. I mean, the galaxies are moving, but we know the galaxies really are just moving with the space, right? So it's an expansion of space and time. So what do you think the value of that might be? What would be your guess? That it might be a constant? What would be your guess? That value of that motion would be? How about c? Wouldn't it be the speed of light? I mean, if you were going to guess one, wouldn't you guess it was the speed of light? You know? Now, it doesn't mean the galaxies are moving out from each other at the speed of light. Actually, some of them are pretty close to it if they're way out. But they vary by the distance from the observer. But the fact that the space is expanding, you think, well, gee, man, that's like a natural clock. That's probably where that constant c comes from, huh? Because light is traveling with that expansion. And that would explain a lot. Well, now, what if we took there's another constant. Anybody have heard of the Rydberg constant? You ever heard of the Rydberg constant? I'm sure you have, right? No? Well,
My physics is 50 years old.
Oh, well, this is going way back too. This is really going way back. But Brady, you know what the Rydberg frequency is.
Yeah, I don't remember.
Okay.
I remember.
Well, it's probably the most tested, observed, established constant there is at physics. I mean, this thing they have nailed down. All right? And it's, when you take it and multiply it by space, you get what they call the Rydberg frequency. Well, what is a frequency? With Rydberg frequency, there's a Rydberg universal constant and a Rydberg frequency for each element. And constant varies for a little bit for each element, but they have what they call the universal constant. They've got that nailed down. But this is pretty constant when you're figuring the spectrum, the atomic spectrum, you know, where light is emitted. That's where light comes from, right? It's always emitted from these changing levels in atoms, in material. It's either absorbed or emitted. But this constant takes there. So that is a frequency. And what is a frequency? I mean, that's a constant frequency. What is a frequency? It's a vibration. It's a vibration. And what are we looking for? Well, we wanted to find a way that we can add the concept of vibration to this expansion. So, if we actually take that vibration, and vibration, of course, covers one full cycle. If we go around, we've gone one unit this way. If we project it on a circle on the diameter, you guys probably can't see it here, but anyway, you got to go twice, up and then down for one cycle. So the length of this is 1/2. 1/2 times the Rydberg frequency, not 1/2 times the Rydberg frequency, but 2 times the Rydberg frequency divided into 1, or its reciprocal, is 1.5198 times 10 to the minus 16 seconds. Well, that's a heck of a lot better than that Planck time. And then, once we have that time, if that's modified, then we can multiply it times the speed of light and get the actual distance that it would travel in that much time. The expansion would take place in that much time. And that comes out to 4.5563 times 10 to the minus 6 centimeters. Wow, that is really within observation. So we've got sort of a string theory, but it's not a string. Because this is not a string. This is not one dimension. How many dimensions is that? That's 3. 3-dimensional, but that means 8 directions, because there's 2 directions in each dimension, right? So 2 to the 3rd power is 8. All right, well, let's talk about 1D dimensions for a minute.
Rock. How does this instrument make its revolutionary, history-changing sound?
My name's Dr. Mark Looney. I've got a PhD in guitar acoustics, and in the next 3 minutes, I'm going to explain the physics of rock guitar. When I pluck a string, it vibrates and makes a sound by moving from side to side.
The pitch of that sound depends on how fast it moves, the fundamental frequency, and that in turn depends on 3 things. 1, its length. The shorter, the higher. When I fret a note, I make the string shorter, so the pitch rises. 2, tension. The looser, the lower. When I press down my whammy bar, there's less tension, so the pitch drops. And 3, thickness. All of these strings are the same length and the same tension, it's just the lower pitched ones are thicker. And to get really low notes, they've got to be really thick, which curiously also applies to bassists. But when you pluck a string, it doesn't just move from side to side. The rich sound you get comes from other patterns, the harmonics. When I rest my finger halfway along the string, so that it vibrates either side of my finger at twice the fundamental frequency, I hear the first harmonic. If I rest my finger closer to the end of the string, a third of the way along, so that it vibrates at 3 times the fundamental frequency, I hear the harmonic of the second kind. Closer again, I encounter the third kind. And so on. If the fundamental's at 100 Hz, the harmonics are at 200,
300, 400, higher and higher, always at the top of human hearing range, 20,000 Hz.
Strings sound nice because these regularly spaced harmonics are all happening at once. Now, on an electric guitar, magnets convert the harmonics into sine wave signals. Problem is, to fill a stadium, we need to boost these signals. Guitarists in the 1960s tried turning the volume up past the fidelity limits of their amplifiers, which started squashing the top of the sine waves. That squashed top gave each harmonic harmonics of its own, and those false electronic harmonics got their own false electronic harmonics. This cascade of harmonics turned the simplest riff into something powerful. So that rock guitar sound isn't a kind of magic. It's just simple physics.
It's not string theory, of course, but it's the basic principle of one-dimensional vibration. Now, when we're talking about 3D vibration, it's facetiously have named it just for this presentation ball theory, because that's what it would be. If this expansion was three-dimensional expanding and somehow reversed, it would collapse like a ball, right? And it would expand and collapse and expand and collapse. And so, if we do that mathematically, we can take this expansion and we get this one over here. If the space aspect of the expansion starts vibrating, oscillating, say, for one period of time, and then reversing and collapsing for one period of time, you get this oscillation here, and that would be 1/2, which would be our fundamental. And then 4 times, which is the same thing as 0.5, right? 4 times that is 2, which is what we get over here. If it's the time aspect of the expansion that's oscillating instead of the space. So you wouldn't be able to tell the difference and notice that somebody was going to say, well, gee, time can't be 3D, and time can't reverse direction and all that stuff. Well, I know, but the mathematics, just like the mathematics of string theory, works out fantastic. And you start to get these octaves, there's 2 octaves in between here. You got this fundamental, first harmonic, the second harmonic, and you add those together. It works out that this might be gravitation, and this might, there's so many things that this could lead to. and I won't get into them now. We're almost out of time, but we will in future lectures. We're going to be talking about how that works and how it fits with the observations and with the current theories. Now, what we want to do is these crucial calculations where we can now take C and R, the speed of light, and the Rydberg constant, and from those derive these. All right? And if we use Borg's dimensional analysis, we see the gravitational constant can be put in this form, which is really exciting because that's like mass squared times time. And we'll get into that a little bit. And this is what the number should be. This is well, it varies, but it's the gravitational constant. It varies by year. And then Planck's constant, H, has these dimensions, and we should be able, using this, to come up with that. That would be fantastic if we could do that. We haven't done it yet. But that's because it's pretty complex when you start thinking about it. But look how interesting this is. If we take this idea, now instead of using mass, length, and time, we're using specifically just space and time. So I don't have length here. S is not seconds, S is space in this sense, and T is time. So we can take Einstein's equation where E, which has dimensions T over S, right? Time over space, or seconds over length, which you're probably used to. We can take the dimensions in mass, multiply them by the dimensions of velocity squared here, and voila, we get the dimensions of energy. We can do the same thing in Planck's constant. Here's H times nu, all right? And the dimensions of that are the dimensions of the quantum action, T squared over S, times the dimensions of frequency, 1 over T, is equal to T over S. So it becomes very clear. And then we can go on, this is crazy stuff, but if we're just doing it mathematically, we're just fiddling around, we can look at the dimensions of G, which then work out like this, and S is 6 over T to the 5th, so dimensionally, mass then, if we just do the simple algebra, becomes T to the 3rd over S to the 3rd, and the inverse of mass, which may not make any sense to anybody right now, becomes S third to over T to the 3rd. So that is really interesting. What is inverse mass? You know, we're looking for gravity to explain gravity, and we have some interesting things to deal with. But we'll talk about those later. Then we can look at the dimensions. It's getting late, but we're past our time here. So anyway, point is, you take the force equation, and you can see that by using the G dimensions and dimensions of mass, they reduce the time over S squared, so that's the dimensions of force. And then these equations show how we get the dimensions of G. So the bottom line is that it seems to be a pretty good idea maybe to fiddle around looking for a natural unit of space and time that is not at the Planck length, at the Planck scale. Whatever these units may be, we know that their quotient, S over T, is the constant C, the speed of light. So that gives us a huge clue. So here's what we're looking for, guys. We want physicists, we want you to grow up and become physicists that can study these 3D nonlinear vibrations, or what I have called, strictly for the first time in this presentation, ball theory, to correspond to string theory. I don't think I'd call it ball theory any more than they call string theory rubber band theory. But we're going to be talking about these things every first Tuesday of each month. And the next Tuesday we'll be talking about the unification of geometry and algebra, the Bott periodicity theorem for the Greek text actress. It's really interesting. Then we'll go on to the foundations of quantum mechanics, origin of spin, uncertainty, and wave-particle duality, combinations of 3D scalar vibrations, preons, and the standard model, energy, momentum, and periodic table of elements. If you guys will give me your email addresses on the back of one of those brochures over there, I will send you my wheel of motion that is in new format for the table of the periodic table of elements. I think you'll find very interesting. And then we'll be talking about gravity and zero-point vacuum energy dilemma, and the Big Bang and the Big Revisiting Implications of Dark Matter and Dark Energy. Tentatively, that's the list of things we want to do in the next 6 months. I hope you'll come. I hope you'll bring your buddies and your teachers. Not one teacher's here. If you've got some here, because they said they would be here. So,
He has something to do tonight.
yeah. Well, anyway, that's it, and appreciate everything, and with that, we'll turn on the lights. Unless you have some questions, anybody have any questions?